So hi everyone. Today we'll discuss chapter 9, which is ideal gas equation of state. So in chapter 8 we discuss Zeroth law and temperature measurements. What are the different methods which are used for taking temperature of a body? Like a reference body is taken and then a thermodynamic property is taken which is changing when the temperature is changing, and that's how you measure the temperature of a body. Similarly, ideal gas equations are another set of equations which are used for thermodynamic calculations. In further chapters, we will recall these equations for our calculations and also to derive further formulas. So let's understand this. What exactly is ideal gas equation? So in real situation, there are two kind of gases, ideal gas or a real gas. Real gas is what we generally encounter in our day-to-day life. Ideal gas is an ideal situation. So whenever we work with science, there is everything an ideal engine, ideal gas. We take a reference point and then we define our laws around it, right? Because to predict the nature of a real material or substance or gas is very difficult. That's why we have to take an ideal condition. Now, what the ideal condition is when we have very low pressure. At that low pressure, the behavior of the gas typically depend on these three quantities, and we can formulate this equation 1, which is PV is equal to RT. Now this is not just PV RT, you can see there is a bar here on V and R. So this is basically your specific volume, not just specific volume, but your molar specific volume. So V is small here, and then you have a bar. So this is molar specific volume, unit for which is meter cube per gram mole. So this is volume per mole, okay? And also we are taking R bar, which is universal gas constant, value of which is 8.3143 joule per mole Kelvin. So again, per mole we are talking about, taking every single molecule into account. And then T is the absolute temperature. So this will be in Kelvin scale. Now, if I divide this equation, and why to divide? Because we want to obtain further resolve this equation to simpler terms, which is more realistic in nature and which we can work with. Because every time specific molar specific volume or molar specific gas constant is available, but molar specific volume will not be available, right? So we divide it with mu, which is molecular weight. The unit for this will be, the SI unit is kilogram per mole. So let's divide this equation 1. This is your equation 1 here. Divide this by mu. So we get molar specific volume by mu, universal gas constant by mu, absolute temperature by mu. So I can cancel these two out. I can also cancel these two out, but what's the point of? It will become again the same equation. So now we will further simplify these two things. Okay, so if I do the dimensional analysis, it is simple to see it in a way to put the units and then solve it. So the molar specific volume is meter cube per gram mole, and you are dividing this by molecular weight, which is kilogram per mole, right? Kilogram per mole, which is the molecular weight. And over here, this will simply become meter cube per gram mole. Mole will go up here, then you have kilogram. So this cancels out. I can express gram in terms of kilogram, 10 to the power minus 3. So in simple terms, the units will become meter cube per kilogram. So this is now my specific volume. Volume is in cube, meter cube. If it was just meter cube, that was my volume, right? Total volume. But if I'm talking per kilogram, so that's my specific volume. So now this small v and bar actually becomes, now becomes V, when we divide it by mu. Okay. Now on the right hand side you have this R bar by mu. So let's simplify this also. R bar by mu. R is universal gas constant. The unit for universal gas constant, we defined it as joule per mole Kelvin. So you have joule per mole Kelvin, and then you divide this by your molecular weight, okay, which is kg per mole. If I simplify this, it becomes joule per mole Kelvin, and this goes here, and I get kg. Again, the same thing. I made this joule per kg Kelvin, or we say kilo Kelvin. So this is my simplification. So now this R bar by mu becomes R. Okay. This V here was specific volume, and this R here is characteristic gas constant. Gas constant. Now please remember, this R is universal gas constant. Universal gas constant, and this is characteristic gas constant. Now, so your final equations become P, we have small v, bar is removed now, this is specific volume. In terms of R by mu, we have simply R, which is characteristic gas constant, and then the absolute temperature. So this is your one equation. Okay, let's say this is equation A. Okay, so this is one form of equation. Now, I want to express this equation in terms of mass and in terms of moles. Okay, so what I'm trying to do here, this is specific volume. Specific volume is, this equation is valid if I have per unit volume, like how much volume is there per unit kg. But what about the total volume? If my volume size is given, if I have pressure and if I have total volume V, capital V, okay, which will be simply, if I say unit of V will be meter cube, and V specific volume is meter cube per kg. So you need the total mass to multiply with, and this will become meter cube here. So what I'm going to do to simplify this equation, I'm taking equation A. I'll keep this here as V, but instead of R, I use this relation here. R is equal to R bar by mu. So instead of this, I just place R bar by mu into T. Okay. Now, P into, this is my specific volume, into mu into R bar by T. R bar into T. Now, if I further simplify in terms of, let's take this thing here. This is meter cube per kg. This is molecular weight, which is kg per number of moles or mole here, which simply becomes, this is gone, meter cube by number of moles, or I can write it meter cube by n. This is moles is denoted by n, which is number of moles. Okay, so I can simply write this equation now. P into, this becomes capital V. This is the total volume now. Okay, and R bar into T, because this mole goes on the right hand side. This is another equation which we obtained. This is equation B. Okay, this is equation A, P, V. V was small here, RT. And this is here PV. Now V is capital, which is total volume instead of specific volume. in terms of number of moles, your gas constant, universal gas constant, and then absolute temperature. Now this can be used to obtain further calculations, right? Because at most of the time you will have pressure, you will have volume of the body, you will have these two units will be known, and the temperature of the body. So if you just know pressure, volume, you can find the temperature. If you know volume, temperature, you can find the pressure. That's how this relation works. Third relation can be obtained in terms of mass. Okay, in terms of mass. So how to obtain in terms of mass? And over here you have this relation volume P into V. Now this equation I'm just simply writing it N into again R bar. Instead of R bar, I use this equation here which said R bar over mu is equal to R. From here I can write R bar is equal to R into mu, right? Which is the characteristic gas constant into molecular weight is equal to universal gas constant. So instead of this R bar, I can simply write characteristic gas constant into molecular weight into T. Okay. So P into total volume of system. This is number of moles. This R bar now is simply R. Okay. And this is molecular weight. So instead of molecular weight, if I write kg per number of moles, or I can write N denoted by N into T. So number of moles is gone. I can simply denote this equation in terms of kg, which is the mass of the body. So let's use term M and T. So this is another equation. PV is equal to mRT. So this set of three equations, equation A, which was P specific volume V R T, then P into total volume V, N number of mole, R bar into T, and then the final equation P into V is equal to mass into R, which is the characteristic gas constant, into the absolute temperature. These three equations are known as ideal gas equation of state. Ideal gas equation of state. And why we simplified and obtained these three different forms of equation? This is basically the same thing. We are just changing the value on the right hand side, left hand side, seeing it in terms of total volume instead of specific volume. Simply because many a times you will have mass available instead of number of moles. Okay, and many a times you will have total volume, so you cannot use this relation. So we are simplifying it for our own calculations. So we will end this lecture over here. If you like the video, please hit subscribe and like the video as well, and feel free to share this among your friends who might be interested in similar content. And we will see in you next video. Probably we'll start with the first law of thermodynamics, and then we will go from there. Thank you guys, and have a nice day.